First of all, it's not our job to impose our wishes or fears on the universe. Our job is to understand what the universe is really like.
What if black holes aren't just cosmic monsters that swallow everything, but secret doorways to other universes? For over a century, scientists have tried to unlock their mysteries, and now we may be closer than ever. From Einstein's equations to mind-bending wormholes and hidden dimensions, this journey into the heart of a black hole will challenge everything you thought you knew about space, time, and reality itself. Carl Sagan wasn't just an astronomer. He was a communicator, someone who had a rare ability to make complex scientific ideas feel personal, even poetic. Through his books and the television series Cosmos, he brought the universe into people's living rooms. But more than anything, he pushed us to ask deeper questions, not just about what things are, but why they matter and how they connect. Sagan believed that science wasn't simply about facts, it was about understanding our place in the cosmos. He often pointed out how small we are, not to make us feel insignificant, but to remind us that humility is a strength in science. It's what keeps us asking questions.
We physicists have waited 100 years since 1916 for this photograph.
One of the questions Sagan returned to over and over again was whether there might be more to the universe than what we can directly see. He spoke about dimensions beyond the ones we experience, about time as something that could curve or stretch, and about the possibility that space itself might be filled with invisible pathways. Ideas that are no longer just speculative, but form the basis of some of the most cutting-edge physics today. In a famous analogy, he described how a two-dimensional being might struggle to understand the concept of height. A creature living on a sheet of paper wouldn't have any reference for the third dimension. It wouldn't even be aware it was missing anything. But if a three-dimensional object passed through that sheet, the creature might catch a glimpse of something it couldn't fully explain. To Sagan, that was how we might relate to higher dimensions or unfamiliar aspects of spacetime. We may see hints of something, but we don't yet have the tools to understand it clearly. That kind of thinking about what lies just beyond the limits of our perception is now central to modern astrophysics. It turns out, the universe hides many of its secrets in ways that challenge the laws of physics as we know them, and perhaps no cosmic object illustrates this better than the black hole. In Sagan's lifetime, black holes were still mostly theoretical. They were predicted by Einstein's general theory of relativity, published in 1915, but not widely accepted as real for decades. It wasn't until the 1960 essay that astronomers started to find convincing evidence that black holes weren't just mathematical curiosities, but actual structures in space. Even then, there were mysterious places where matter disappears, where light can't escape, and where time itself seems to break down. Sagan often speculated about what might be inside a black hole, though he admitted no one really knew. Today, thanks to research that spans decades and involves scientists around the world, we've come closer than ever to uncovering some of those secrets. And while many questions remain, our understanding has taken huge leaps forward. Modern observations have confirmed that black holes do, in fact, exist. We now know of dozens in our galaxy alone, and astronomers estimate there could be more than 100 million black holes in the Milky Way. Some are the remnants of massive stars that collapsed under their own gravity. Others, known as supermassive black holes, sit at the centers of galaxies and contain the mass of millions or even billions of suns. Perhaps the most famous black hole to date is the one at the center of the M87 galaxy. In 2019, scientists working with the Event Horizon telescope captured the first direct image of a black hole's event horizon, the boundary beyond which nothing can return. This was a major milestone, not just because it gave us a visual confirmation, but because it opened the door to new kinds of research. This growing knowledge builds directly on the kind of curiosity Sagan encouraged. He believed that science progresses by questioning assumptions and testing ideas, even if they seem outlandish at first. In his time, few scientists took wormholes seriously. These are theoretical passages through space-time that could, in principle, connect distant regions of the universe. Today, wormholes are the subject of real scientific investigation, not because they've been observed, but because they are logical extensions of general relativity and quantum mechanics. Physicists like Kip Thorne and Michio Kaku have picked up where earlier thinkers left off, exploring ideas that might one day explain not just black holes, but the very structure of reality. Some of their theories propose that inside black holes, instead of being crushed at a single point, matter might pass through a kind of tunnel, what's known as an Einstein-Rosen bridge, and emerge elsewhere, possibly even in a different universe. These ideas remain speculative, but they are mathematically sound. They've also been supported by newer theories such as string theory, which suggests that all matter and energy arise from tiny, vibrating strings in higher dimensions. If true, this could mean that space-time itself is far more complex than we currently understand. Some versions of the theory even suggest the universe began not with a single explosion, but through the collision or interaction of other universes in a higher dimensional space. This way of thinking fits with Sagan's insistence that science is not static. It evolves, it adapts, it makes room for new evidence, and discards old ideas when they no longer serve. He was wary of certainty, especially in fields that are still developing. Absence of evidence, he once said, is not evidence of absence. This applies just as well to black holes, wormholes in the shape of space-time, as it does to the search for life elsewhere in the universe. In that spirit, it's worth asking what role black holes might play in the broader structure of the cosmos. Are they simply dead ends, regions where information vanishes forever, or could they be keys to something deeper, something we haven't yet grasped? Sagan was fond of the idea that nature is often more imaginative than we are, and modern physics seems to be proving him right. The research into black holes today is no longer about proving they exist. It's about figuring out what they're made of, how they evolve, and what they might reveal about the laws of nature. The more we learn, the more it seems that black holes challenge not just the details of physics, but its foundations. The rules we thought were unbreakable begin to bend. Gravity, time, space. These aren't fixed elements, but dynamic features of a larger, possibly multidimensional reality. Sagan might not have lived to see these discoveries, but he helped create the mindset that made them possible. His message wasn't just to look outward, but to look closely, to treat each unanswered question not as a dead end, but as a starting point. That's exactly the attitude today's physicists are bringing to black holes. Black holes are among the most fascinating and extreme objects in the universe. There are places where gravity becomes so strong that it warps the very fabric of space and time. For much of modern scientific history, black holes were purely theoretical, predicted by equations but not seen or confirmed. Now, they are recognized as a real and powerful part of the cosmos, central to understanding not only stars and galaxies, but also the nature of space-time itself. The concept of a black hole first emerged from Albert Einstein's general theory of relativity, which he published in 1915. Just a year later, in 1916, German physicist Karl Schwarzschild presented a solution to Einstein's equations that described a point in space where gravity would be so intense that nothing, not even light, could escape. This hypothetical point was the beginning of what we now call a black hole, though at the time, the term hadn't yet been coined. For decades after, black holes remained a theoretical curiosity. Many physicists found the idea too strange or too extreme to be real, but that began to change in the 1960s when astronomers detected a peculiar source of X-ray in the constellation Cygnus. This source, later named Cygnus X1, was a binary system, two celestial bodies orbiting one another. One of them was an unusually bright blue star. The other, however, was invisible. What made the system especially interesting was that X-rays were being emitted in large amounts, and these emissions behaved in a way that suggested they were coming from matter falling into a very dense, compact object. After extensive study, astronomers concluded that the invisible companion of the bright star in Cygnus X1 was a black hole, an object so dense that it could not be seen directly, but whose gravitational influence on nearby matter was unmistakable. This was the first strong evidence that black holes were real. Since then, many more candidates have been discovered, both within our galaxy and beyond. Black holes vary greatly in size and type. Some are believed to be only a few times more massive than the sun, while others, known as supermassive black holes, can contain the mass of millions or even billions of stars. These supermassive black holes are found at the centers of galaxies, including our own Milky Way. The one at the center of the Milky Way, known as Sagittarius A, is about 4 million times more massive than the sun. Despite their name, black holes are not empty spaces. Rather, they are regions of space where a large amount of matter has been compressed into a very small volume. This concentration of mass creates an intense gravitational pull. The point at the center of a black hole, where all of this matter is thought to collapse, is called the singularity. It's a region where density becomes infinite, and where the known laws of physics can no longer reliably predict what will happen. Surrounding the singularity is the event horizon, the boundary beyond which nothing can escape. If light crosses this boundary, it can't come back. This is why black holes appear. Like no light that enters can ever return. So the object itself cannot be observed directly. Instead, scientists study black holes by observing how they affect nearby matter, such as gas and dust, and by detecting the high energy radiation emitted as material is pulled in. In 2019, a major milestone in black hole research was achieved. Using a network of radio telescopes around the world, known as the Event Horizon Telescope, scientists captured the first image of a black hole's shadow. The target was the supermassive black hole at the center of the M87 galaxy, which is more than 50 million light years away. The image showed a bright ring of gas and dust surrounding a dark center, the silhouette of the event horizon. This breakthrough confirmed predictions made by general relativity and provided a new way to study these objects. Black holes aren't just strange because they trap light. They also seem to challenge our understanding of how space and time behave. For instance, near a black hole, time moves more slowly compared to areas farther away. This isn't science fiction, it's a well-documented effect of general relativity known as gravitational time dilation. The stronger the gravitational field, the slower time appears to pass. Near the event horizon of a black hole, this effect becomes extreme. To a distant observer, time for someone falling into a black hole would appear to slow down almost to a stop. This leads to one of the more unsettling aspects of black holes, the idea that if something or someone were to fall in, it would be stretched out by gravitational forces in a process sometimes referred to as spaghettification. The difference in gravitational pull between the top and bottom of the object becomes so large that it would be pulled into a thin, elongated shape. This dramatic effect only adds to the black hole's reputation as one of the universe's most violent environment. It's important to note that not all black holes are the same. They can spin, they can have charge, and they can vary in mass. Some may form from the collapse of a single star, while others may have developed in the early universe from dense regions of primordial matter. And though they share basic features, such as the event horizon and singularity, the way they behave can differ depending on their surroundings and characteristics. Even though black holes are incredibly difficult to study directly, they continue to reveal information about how the universe works. The radiation emitted by matter falling into a black hole can be observed from great distances. The way stars move around in visible points in space can suggest the presence of a black hole. And gravitational waves, ripples in the fabric of spacetime caused by massive collisions, have recently given us a new way to detect when black holes merge. Gravitational waves were first detected in 2015 by the LIGO Observatory. These waves, predicted by Einstein a century earlier, confirmed another key aspect of general relativity and gave scientists a powerful tool for studying black holes. When two black holes spiral into each other and merge, they release energy in the form of gravitational waves that travel across the universe. By measuring these waves, researchers can learn about the masses of the black holes involved and how they interacted. So far, all attempts to explore the inside of a black hole have remained theoretical. There is no current way to send a probe or signal past the event horizon. Any object that tries to enter will be pulled inward with such force that it cannot escape. This presents a major obstacle for scientists who want to understand what actually happens beyond that boundary. As a result, much of what we know about black holes is based on indirect evidence, mathematical models, observations of nearby matter, and the effects of their immense gravity. Still, the consistency of these observations across different black holes and different parts of the universe strongly supports their existence and many of the features predicted by theory. There are also many questions that remain unanswered. What really happens at the singularity? Can information ever escape a black hole, or is it lost forever? Could black holes be connected to other parts of the universe? These are questions that physicists are still working to answer, and some of them will be explored further in the coming sections. At the most basic level, a black hole is defined by three main regions: the event horizon, the photon sphere, and the singularity. These layers form the basic outline of how a black hole operates, although each is incredibly difficult to study directly. The outermost region of a black hole is the event horizon. This is perhaps the most well-known part, often described as the point of no return. Once something crosses this boundary, it cannot escape. Not light, not information, not even time as we experience it. The event horizon is not a physical surface, but a mathematical boundary in space. It marks the limit at which the escape velocity, how fast someone would need to travel to break free from the black hole's gravity, equals the speed of light. Since nothing can move faster than light, anything that crosses the event horizon becomes trapped. What happens beyond this point remains unknown. Because light cannot escape, no information from inside the event horizon can reach observers outside. This creates one of the biggest problems in physics, the loss of information. According to the laws of quantum mechanics, information about a physical system should never be destroyed. Yet if black holes truly trap everything forever, it seems this rule is broken. This contradiction has led to major debates and theories, including the idea that information might somehow be preserved in a scrambled form at the event horizon, or even released back into space through processes like Hawking radiation. Just outside the event horizon lies the photon sphere, a region where gravity is so intense that light itself is forced to travel in curved paths. In this zone, photons, or particles of light, can actually orbit the black hole. However, this orbit is unstable. A tiny disturbance can send the light spiraling either into the black hole or away into space. While we can observe the photon sphere directly, it plays an important role in how black holes are detected. The light bending in this region helps shape the shadow that telescopes like the Event Horizon Telescope are able to capture. As moving inward, we eventually reach the singularity, which sits at the core of the black hole. This is the point where the density of matter becomes infinite and the known laws of physics break down. At the singularity, space and time cease to behave in any way that we currently understand. Gravity becomes so intense that no existing theory can accurately describe what happens. This breakdown of physical law is not just a curiosity. It's a signal that our current models are incomplete. A complete theory of gravity, one that combines general relativity and quantum mechanics, may be needed to fully understand the singularity. One of the more unsettling implications of the singularity is that time itself ends there. If you were somehow able to survive falling into a black hole, which current physics says you wouldn't just be crushed by gravity, you would also reach a point where time stops. This isn't just poetic, it's a mathematical conclusion drawn from Einstein's equation. Despite the dangers and impossibilities of visiting a black hole directly, scientists have found creative ways to study them. Since we can't send spacecraft into black holes or observe their interiors directly, researchers focus on indirect evidence. This includes radiation emitted by matter as it spirals inward, distortions in nearby starlight, and patterns of gravitational waves produced by black hole collisions. These methods have led to incredible discoveries. For example, astronomers now know that when matter falls toward a black hole, it doesn't disappear instantly. Instead, it forms what's known as an accretion disk, a swirling disk of gas and dust that heats up as it approaches the event horizon. This disk can reach temperatures of millions of degrees, emitting X-rays and other high-energy radiation that can be observed from Earth. The study of these emissions helps scientists understand the environment around black holes and gives clues about their behavior. In 2021, the Event Horizon Telescope team released new observations of the M87 black hole. By capturing data over several nights and combining the results, they managed to create a clearer image of the region surrounding the event horizon. This provided not only visual confirmation of the black hole's shadow, but also insights into how matter behaves at the edge of a gravitational collapse. Even though these images are composed of radio data rather than visible light, they are among the most detailed views we have of black holes to date. They confirm that black holes are not just empty regions, but dynamic, layered systems governed by extreme physics. One of the biggest challenges in studying black holes is that each one seems to be different. While they may follow the same general rules, having an event horizon, a photon sphere, and a singularity, their behavior can vary dramatically depending on their mass, spin, and the matter around them. Some black holes spin rapidly, which affects how matter moves near them. Others are relatively quiet with little accretion activity. This variability makes it difficult to build one-size-fits-all models. Instead, scientists develop specific simulations based on the characteristics of individual black holes. These models often rely on powerful computer programs that simulate how matter and energy move under extreme gravitational conditions. Another issue is dimensionality. Black holes are three-dimensional objects, but much of the data we gather is two-dimensional. Telescopes collect flat images or measure energy levels, and scientists must then reconstruct a 3D understanding from this limited information. This is like trying to understand a sculpture from a single photograph. It's possible, but much is left to interpretation. This problem becomes even more complex when considering the potential influence of additional dimensions beyond the three of space and one of time that we experience. Some theories, particularly in string theory and higher dimensional physics, propose that black holes might behave differently if more dimensions exist. In those models, the singularity might not be a point but a loop or even a higher dimensional surface. While these ideas are purely theoretical, for now, they could one day provide answers to questions that current physics cannot resolve. There is also the possibility that black holes do not destroy everything that falls into them. Some physicists believe that matter might be stored in a way that could one day be recovered, or that black holes could lead to other parts of the universe through structures known as wormholes. These ideas, while speculative, are supported by some solutions to Einstein's equations, particularly those involving rotating black holes. The study of black holes is still full of unknowns. What is clear, however, is that they are not simple objects. They are structured, layered, and dynamic. Understanding them requires not just advanced telescopes and complex equations, but also a willingness to question basic assumptions about space, time, and reality itself. A wormhole is a hypothetical tunnel through space-time that connects two distant points. The idea was first introduced in the 1930s by Albert Einstein and Nathan Rosen, based on Einstein's own equations of general relativity. Their version of a wormhole, now often referred to as an Einstein-Rosen bridge, suggested that under the right conditions, space-time could be curved in such a way that a shortcut might exist between separate locations in the universe. If this were possible, travel through a wormhole could allow one to bypass the traditional limits of speed and distance, essentially offering a path between points that would otherwise take millions of years to reach. While no wormholes have ever been observed, the mathematics behind them is sound. Some versions of black holes, especially those that spin, appear to allow for such structures to exist, at least temporarily. In 1963, New Zealand mathematician Roy Kerr provided a solution to Einstein's equations that described a rotating black hole. Known as the Kerr metric, this model suggested that spinning black holes might form a ring-shaped singularity instead of a single point. This ring could, in theory, allow for a path through it, possibly leading to a different region of space or another universe. The outer region surrounding this spinning ring is called the ergosphere. In this area, space-time is dragged around by the rotating black hole, an effect known as frame dragging. Within this region, all objects are forced to move in the direction of the black hole's spin. The ergosphere may be key to understanding how energy might be extracted from a rotating black hole, and it also plays a role in some theories involving wormholes. Although the idea of traveling through a black hole via a wormhole has become popular in science fiction, it remains highly speculative in real science. One of the main problems is stability. Most theoretical models of wormholes suggest they would collapse very quickly after forming, unless held open by some kind of exotic material with negative energy density. This kind of matter has never been observed in practice, although it has been theorized in certain quantum field models. Without it, wormholes would not remain open long enough for anything to pass through. Even if a wormhole could be stabilized, there are still major problems to solve. The amount of energy needed might be far beyond anything we can currently produce. Also, the intense radiation and gravitational forces surrounding the entrance to a black hole would likely destroy anything trying to enter, including spacecraft or signals. So, while wormholes remain an interesting and valid area of research, they are not yet considered a viable means of transport or communication. Another important question concerns the apparent contradiction between general relativity and quantum mechanics. These two pillars of modern physics describe very different aspects of the universe. General relativity explains gravity and the large-scale structure of space-time, while quantum mechanics governs the behavior of particles and forces on the smallest scales. Black holes appear to be where these two frameworks collide. One of the main issues is the singularity at the center of a black hole. General relativity predicts that everything falling into a black hole is crushed into an infinitely small point with infinite density. But quantum theory does not allow for such infinities. This conflict has led physicists to believe that a new unified theory is needed, one that combines both gravity and quantum mechanics into a single framework. This is often referred to as a theory of quantum gravity. One of the leading candidates for this theory is string theory. Unlike traditional models of particles, string theory suggests that the most basic building blocks of reality are not point-like particles, but tiny vibrating strings. These strings can vibrate in different ways, producing the different particles and forces observed in nature. One of the remarkable features of string theory is that it naturally includes gravity. In this framework, gravity is not a separate force, but an outcome of how strings interact in higher dimensional space. According to string theory, the universe is not limited to 3 spatial dimensions and 1 time dimension. Instead, it may contain as many as 10 or 11 dimensions, most of which are curled up so tightly that they are invisible to us. The presence of these extra dimensions allows for a much richer and more flexible model of reality, one that could potentially explain phenomena like black holes and wormholes in a new way. Some versions of string theory also predict that our universe might be just one of many, a single bubble in a vast multiverse. These other universes could have different physical laws, different dimensions, and even different concepts of space and time. In this picture, a black hole might not just destroy matter, it might serve as a kind of bridge or seed from which a new universe can emerge. Some physicists have even proposed that the Big Bang itself could have been triggered by a black hole in another universe, connecting the ideas of cosmology and quantum gravity in surprising ways. One of the most fascinating possibilities is that our entire universe could exist inside a black hole. From the inside, space would appear to expand, as it does in our observed cosmos. From the outside, the black hole would seem like a compact, dark object. This idea is difficult to test, but it shows how black holes challenge our understanding of what a universe is and how it might begin. Despite the promise of string theory, it remains unproven. The mathematics is incredibly complex and direct experimental evidence is still lacking. Some progress has been made, such as showing how string theory can resolve some paradoxes related to black holes in simplified models. For instance, recent work has suggested that string theory may be able to explain how information is preserved in black holes, avoiding the contradiction with quantum mechanics, but many questions remain. Physicists continue to explore other paths as well. Loop quantum gravity, for example, is another theory that attempts to merge gravity with quantum mechanics. It uses a different mathematical approach, treating spacetime as being made up of tiny loops. While this theory also shows promise, it faces similar challenges in terms of experimental testing. Ultimately, what we do know is that black holes are not just cosmic oddities. They are central to some of the most important and unresolved questions in modern science. Whether they serve as keys to new dimensions, connections to other universes, or laboratories for testing the laws of nature under extreme conditions, black holes push our understanding to its limits. As more advanced observatories and experiments come online, from next-generation space telescopes to gravitational wave detectors, we may soon find new evidence that helps confirm or challenge these theories. Until then, black holes remain among the most powerful and mysterious features of the universe, a gateway not only to destruction but possibly to deeper knowledge. And perhaps, as Carl Sagan once implied, the answers to these mysteries are not just out there among the stars, but within the very questions we dare to ask.